assuming, especially because we're about to do this. And I got a 9 out of 10. I was interested about all this time. I got 9 out of 10. I was like, yeah.
Okay, good morning everyone. Good morning. All right, now the exam is closed for everybody. Okay. What did you think of the exam? Yes?
I'd say it was shockingly, I wasn't expecting to work for 4 hours like constantly, but I think the 4 hours wasn't like crazy. It was like for, I don't think I could have finished it in 2 hours, I guess.
Neither could I. Which is why the 4 hours is necessary. Alright, and what you will see is that the exam problems are not going to be similar to your homework problems or your practice exam problems, because this is supposed to be an exam. It's supposed to be a test of your comprehension of how much you've understood, and this goes for the entire class, of course, how much you've understood as we are going through this semester. And let me also mention that I try to solve as many problems as I can, but unfortunately we do not have any recitations for this course, and as a result I am limited in the amount of time I can spend on solving different types of problems. I also have to teach concepts. This is not statics or dynamics where we just keep solving problems, right? So we've got to learn things, understand the foundational aspects, and then employ that particular mentality in solving your problems. Okay? So if at all anything this course teaches you, is it teaches you to be brave when facing unforeseen situations. When you come across problems that you may not have an idea of how to solve, a course like this will teach you the necessary skills that you need to develop. Okay? That's the expectation. The final result is up to you. Okay. So I'm going to move on. I'm going to spend a couple more lectures on conduction, heat transfer, and then we'll move on to radiation. I want to solve a problem on fins today. You don't have a homework due this week, but nevertheless I'm going to post the homework that is due next week, early this week, so that if some of you have time on your hands, you can start working on it. Okay? Alright. Exam grading will typically take a week and a half. So you can expect your papers to be handed to you, not handed but uploaded on Carmen. I'm the one who grades your exams. You will typically get this back sometime in the middle of next week. Okay? And I appreciate your patience as I spend time reading your answers. Okay, so I'm going to talk about the third case of the fins, and then we will look at a problem that belongs to none of the cases we have looked at. So case 3 for fins. The first case was the fin was infinitely long. Okay? The second case was the fin was having an adiabatic tip. And the third case is where the end of the fin is open to convection. So fin open to convection with the ambient. It does not change the foundational equations for the fin. That still remains the second order ODE that we've looked at. So the fin equation where theta is a function of x, theta is a non-dimensionalized or a change of variables, not non-dimensionalized, change of variables. t of x minus t infinity. Okay, and then this m squared is the following set of numbers grouped together. H is the heat transfer coefficient, convective heat transfer coefficient. P is the perimeter of the fin. Kf is the thermal conductivity and of the fin material, and then A suffix C is the cross-sectional area. Okay. Solution. Theta of x is an exponential solution here. So two constants, C1, e to the power mx, C2, e to the power minus mx, and the whole basic idea of fins is, okay, I have all these equations, I have the general solution. What are the boundary conditions that will enable me to solve for C1 and C2? Okay. There is always a typically standard boundary condition that is prescribed for all fins. That is the temperature at the base of the fin. The boundary conditions. So T at x is equal to 0, which is called the base temperature. This is always prescribed. And so this tells me that theta is theta b, Tb minus T infinity. So this is the first boundary condition. Okay. Second boundary condition. The tip of the fin is open to conversation with the ambient surroundings. Okay, so if I draw the figure, right, so this is the wall material where the fin is embedded. This is x is equal to 0. X is equal to L. The temperature at the base is prescribed to us, typically T suffix B. And the second boundary condition is that if I draw a control surface at the tip of the fin, T infinity and H, big assumption is that this heat transfer coefficient is the same on all regions that the fin is in conversation with the ambient atmosphere. Okay? Need not be the case, but we will assume that to be the case. Alright, so this is the second boundary condition where you perform a surface energy balance. I have conductive heat flux coming in. This is Q double prime conduction at x is equal to L. This is coming in through the fin material, and then this is going to be convected out onto the ambient. Q double prime convection. So if I write this out as a boundary condition, okay, multiplied by the cross-sectional area, so the second boundary condition is minus K fin AC d theta by dx, which is the conductive heat transfer rate, not the flux. This is evaluated at x is equal to L. This is equal to the convective heat transfer rate, which is H times A cross section, because I'm looking at the conversation between the tip of the fin and the ambient, and the area available for heat transfer there is the cross sectional area. Okay? And this is multiplied by T at x is equal to L minus T infinity. Alright. And if I do the substitution of these boundary conditions, I have already done it in the lecture notes which I posted on Friday. I'm just going to write the solution. So after you substitute theta of x by theta b, which is the difference between Tb and T infinity, this ends up being 4, right? Cos hyperbolic plus sin hyperbolic numerator. It's a kind of a nasty derivation, so I'm not going to do this. And this is cosine hyperbolic h by kf times m. Hyperbolic sine. Please look at my notes where I have done this derivation. It is just a question of plugging in and then doing some algebra. It is not earth-shattering. It is just a simple expression which looks complicated because it has gone through a lot of steps. Okay. Then the heat loss rate, which is nothing but the heat that is conducted into the base of the fin. Q conduction at x is equal to 0. If you go through the math, this is essentially going to be minus kf cross section d theta by dx at x is equal to 0. Substitute, solve for Q loss. This is what you end up getting. So Q loss is capital M sine hyperbolic L minus x h by kfm cosine hyperbolic L minus x by the same denominator as you had for the temperature ratio there, which is cosine h ml h by m kf. Okay. I want to point out, last class we looked at infinitely long fin, and essentially it is a limiting case of an adiabatic fin. We solved the problem to its entirety, to its completion. We can solve a similar problem where instead of having an infinitely long fin, you have ambient conditions prescribed at the tip. You perform the energy balance and then you substitute and solve for the coefficients. It's fairly straightforward, it is just a substitution. So I'm not going to solve a problem on case 3, you'll have one on your homework. It is the exact same path that we have taken for solving infinitely long adiabatic fins. Okay, nothing spectacular there. But I want to solve a different problem. So in this problem, I have a fin performing a dual purpose. Not only is it cooling one surface, but it's actually in contact with another surface, and so it is drawing out the heat from the other surface as well. So this is a double cooling fin. Okay, I'm going to draw the sketch. So there is a circular rod that is embedded partly into the wall. Insulated, okay? So a portion of this rod is embedded into the wall. The other portion is in contact with a different material, which means that there is going to be a certain contact resistance between the tip of the fin or the tip of this rod here. We haven't figured out if it's a fin or not. There's a certain contact resistance between the tip of this rod and the other source. Okay? I'm going to draw that as a thin infinitesimal strip, and then I have another source here. The following information is given. Okay? So temperature here is 200 degrees Celsius. Then you're told that the total length of this body is 100 millimeters. So starting from here, I'm going to set up a coordinate system. Typically, when I set up a coordinate system for a fin, I want the fin to start beginning at x is equal to 0 because it simplifies a lot of things for us. Okay, it is just that there is nothing special about coordinate systems either. Okay, so this is x is equal to 0, 50 millimeters minus 50 millimeters or 0.05 meters. So this is the setup that is given to you. the contact resistance is prescribed. So R double prime is 4 times 10 to the power minus 4. Look at the units. Kelvin, meter square by watts, which means that you have to divide by the area to get the actual thermal resistance. Okay? And then you're told that the temperature of this surface is 100 degrees Celsius. So that's the temperature at the other end of this surface. It's not the temperature at the end of the rod. Please notice there is a small gap between the rod. It's not a gap, it's essentially a contact region, which is modeled by the surface roughness of these bodies coming in contact. That temperature is 100 degrees Celsius, and then I'm given some other information as well. Let me adjust my mask if you don't mind. With all this adjustment, it's practically worthless wearing one. Alright, but it's always useful to wear one. Okay? Alright, now we move on, and I say that the thermal conductivity of this rod material is given to me. So K is 100 watts per meter Kelvin. This entire rod, there is an embedded portion here, so I'm going to call this E. Like last time. This is the protruding portion. I'm going to call it as F. The diameter of the rod is given to me, 5 millimeters. And then the temperature at the ambient conditions is given to me as 20 degrees Celsius. So T infinity, 20 degrees Celsius. And I believe that's all the information that we have in this particular problem. Alright. And what we need to find out, what's the temperature profile? Okay. So, temperature profile, and then the heat flux profile. Very interesting figures, both of them. Okay. First things first. Look at the portion that is embedded within the wall. Even though this is a cylindrical body, you see that the top and the bottom are insulated. The side is also insulated, which means that the only way that heat can travel is along the length of the embedded portion. And because that is the case, and because the travel of heat is not perpendicular to the length here, it's not radial, so we are still going to consider the embedded portion as a plane wall. Okay? This is a similar argument that we espoused last time we met. Then I look at the protruding portion. Obviously the letter F is a clear giveaway that this is a fin, but just to make sure that we are all on the same page, the direction of heat transfer due to conduction, one-dimensional, along the length of the protruding portion is along the x-axis. The direction of convective heat transfer is perpendicular to it, along the top and the bottom sides, all along the surface area. And so the direction of heat transfer is due to conduction perpendicular to that of convection, so the protruding portion is a fin. Which means the fin equations are applicable here, the plane wall equations are applicable here. So this is plane wall. This is the fin portion. And that's something else. We don't know, we will figure it out. Alright, so for this situation, we cannot do the following. We cannot say that this is infinitely long because it is actually in contact with some other body. The condition for an infinitely long fin is that its temperature at the tip will reach eventually ambient conditions. That's absolutely not the case here because it's touching a hotter body. We also cannot say that the tip is adiabatic because obviously that's not the case here. We also cannot say that the tip of the fin is open to ambient conditions, so it does not belong to either case 1, which was adiabatic, case 2, which was infinitely long, or one of the other, and then case 3. So this is belonging to none of the cases, which means that we have to start from scratch. We have to set up the problem, use the solutions that we already have, that is C1 e to the power mx and C2 e to the power minus mx and so on, but look at the boundary conditions and apply them very carefully to this problem. Okay? So the given fin does not belong to any of the cases we know. There is no mention of heat generation, so heat generation is 0 everywhere. That's an assumption that I'm going to make as well. In the last lecture, there was heat generation within the embedded portion, and there was nothing in the fin. You will not have heat generation in the fin because it is our assumption that the fin does not undergo any heat generation. Okay? Start off with the plane wall section. This is minus L, I'm going to call it as L here. Okay, so this is x is equal to minus L. X is equal to 0. X is equal to plus L. So between minus L and 0, I start with the HDE, the heat diffusion equation, one dimensional. The embedded portion has the same thermal conductivity as the fin portion. So KE is the same as KF. And so I'm just going to call it as K. So K times d square dE, dx square is 0, steady state. This is trivial. We've done this many times. The profile is linear. If the profile is linear, the flux is constant. That's also something we know. Then I go to the fin portion, which is from 0 to plus L. I'm not going to start with the HDE because we have already done all the hard work. We have applied the HDE to obtain the fin equation, and then we have also solved for it by getting this exponential solution. I'm just going to directly appropriate the exponential solution. Look at this. Theta is, I'm going to call it as some C3 tilde. Okay, so watch this. C3 tilde e to the power minus plus mx e to the power minus mx. Same type of solution. Theta is T minus T infinity, so T fin is T infinity plus, and this is going to be C3 or whatever, all of those things. Okay, so C3 e to the power mx if you want, you can lose the tilde. I'm just differentiating it by saying, okay, these are constants that belong to the fin, those two are constants that belong to the plane wall. There is nothing special about the tilde. Okay? If you want, we can lose it. It just looks scary. Okay, so this is the profile that I have. Two equations, four constants, which means I need four boundary conditions. So in the hunt for four boundary conditions, here is what we will think of. Okay? I need to find C1, C2, C3, C4. The first boundary condition comes from the fact that the temperature at x is equal to minus 0.05 is prescribed. That's the first one. The second boundary condition comes from the fact that at x is equal to 0, the temperature of the fin at x is equal to 0 is the same as the temperature of the plane wall at x is equal to 0. The third boundary condition comes from the fact that if I perform a surface energy balance at x is equal to 0, the conductive heat flux from the plane wall is equal to the conductive heat flux going into the fin. The fourth boundary condition is the sticky creature. It has to come from this arrangement right here. and we will look at it eventually. Okay? I'm going to start with the first boundary condition. So 4 unknowns. You need four equations for a deterministic system. Start with the first one. And x is equal to minus 0.05, the temperature is prescribed 200 degrees Celsius. TE at 200 degrees Celsius. And if I look at the substitution, C1 times minus 0.05 plus C2 is 200. So my first equation. So minus 0.05 C1 plus C2 is 200. Second and third boundary conditions are also fairly straightforward. At the fin wall interface, and x is equal to 0, I have continuity. Okay. So this is TE is TF. Wherever I see an x, I substitute 0. E to the power 0 is 1. E to the power minus 0 is also 1. And so I have the formula. C2 is equal to T infinity plus C3 plus C4. T infinity is 20 degrees Celsius, so I'm going to do the substitution. So C3 plus C4 is C2 minus 20. During your exam, I saw some confusion for some folks. Do I work in degrees Celsius or do I work in Kelvin? If you're doing problems that involve only conduction and convection, it makes no difference. If you include radiation, then Kelvin becomes critical. And thankfully, your midterm did not have any radiation problems. Okay, so you're welcome. All right. Third boundary condition, same interface. Conductive flux from the plane wall is the same as that onto the fin. So Q double prime is equal to Q double prime fin. Watch out here, sometimes it is possible that the fin material need not be the same as the material of the wall, and so there could be a discontinuity, slope discontinuity. In this problem, and I need to make a correction from last time, I did send a note about that. If the material discontinuity is not present, if the conductivities are the same, you're going to have the temperature being continuous, obviously. The slope of the temperature will also be continuous between the wall and the fin. Okay? Alright, so I do the substitution. So minus K dTE by dx is minus K F and E dTF by dx. KE and KF are the same. The area of cross section is also the same, which is why I did the flux balance. And if I do the substitution, so this is what we end up getting. So dTE by dx is just C1. And dTF by dx, I take the exponential profile, differentiate it once, I end up getting C3m e to the power mx minus mx at x is equal to 0. When x is equal to 0, both of these creatures become equal to 1 in the sense. So C1 is m times C3 minus 0. While we are at it, let us calculate this m fellow. Okay, It's a combination of all of these fin, geometry, and material parameters. So m square h p kf ac, and the heat transfer coefficient, I believe I did not write it there, but please note its value. This is approximately 100 as well. So h is given as, this is given. Okay, this is m square. Please do not forget to take the square root. So this is 100 times the perimeter. This is a circular body. The diameter is given, so the perimeter is pi times d, divided by 100 times pi by 4, 0.05 square. Then you take the square root of all of these to get m. Approximately 63.2. The units are 1 by meter. Okay. So if I see little m, I substitute 63.2. Okay. So I have three equations. I need one more, and then we are all set. It is just a question of solving them. Any questions so far, please? Once again, there is nothing to this problem, essentially. You go methodically, you set up the coordinate frames. X-axis is the only axis of interest here. Recognize that one portion is the plane wall. Recognize that the portion protruding out is the fin. Employ the boundary conditions. Look at the data that is given to you. Temperature at the left end is given to you. At the interface between the wall and the fin, I have two boundary conditions. Now we set out to seek this last elusive boundary condition. Last boundary condition. Now you see, once again, this is a common issue, right? Typically in heat transfer is, how do I know what is the direction of heat flow? I don't. I trust my math. Because these equations have been obtained historically by every single major player in the field of heat transfer, and they have seen to work. If you follow these to a T, you will not be worried about the direction of heat transfer. The direction of heat transfer will present itself to you. Okay? So what I'm going to say is the following. Even though I know that the purpose of a fin is to cool things, at least the fins that we are looking at, I'm going to say that the direction of heat flux at the tip of the fin is from the fin onto that source. If I am wrong, what will end up happening is that I will get a negative answer, which is completely fine with me. Okay? So I'm going to draw the tip of the fin, then the contact resistance there, then we have the source. Just drawing it as a large body here. This is infinitesimally thin. Okay, this essentially is the surface roughness profile interface at the interface between these two bodies, and then here I have the source. This is x is equal to L. This is the tip of the fin, and if I draw a control surface in the following nature, I know for sure that the temperature of the fin at x is equal to L. So here, this is not the same as the temperature of the surface, because that temperature is at 100 degrees Celsius, because of the fact that there is a contact resistance. So there is going to be a discontinuity in the temperature profile there. Okay, so in this case, this temperature, I'm going to call it as T suffix S, which is the temperature of the surface, as 100 degrees Celsius. It's given to me. I'm going to assume that the direction of heat flux is in the positive x direction. I don't know. I will be wrong. I hope to be wrong, because this is a cooling fin. So this fin has to take in heat from the wall and also take in heat from the other source, And so there is probably a point of inflection if I look at its flux profile. Okay, so we will see, we'll figure it out. Here is the conductive flux that's entering through. And obviously there is some flux that's going out. Q double prime at the surface. And from surface energy balance, we know these two are the same. So Q double prime fin is equal to this is from surface energy balance. And because of the fact that within this contact resistance region, which is infinitesimally thin, there is no heat generation whatsoever, I can actually draw a thermal network between the tip of the fin and the temperature at the other end of that surface, 100 degrees Celsius, and the resistance there is going to be the contact resistance. Okay, so if I draw it out, why am I able to draw it? Is because it is the same flux that is entering the control surface and then leaving at the other side of it because of the surface energy balance. Okay, so if I now write this out, this is T fin and x is equal to L. This is Ts. The contact resistance I have to divide it by the area, so this is R double prime divided by the area of cross section. Okay, and then whatever is the variable that's flowing through it, the current variable is the heat transfer rate, Q fin, and x is equal to that. This is what is flowing through this resistor due to the temperature difference or the potential difference between the ends of the resistor. And if I unpack this, Q fin at x is equal to L is the following. Is the difference in temperature divided by the thermal resistance to conduction or convection, whatever is taking place. This is the contact resistance. So R divided by AC. Unpack this further, one more equation will come out. And so, Q fin minus K times area of cross section dt by dx at x is equal to L. So minus K times AC dt by dx. I'm going to cross multiply that contact resistance and bring it onto this side. So this is multiplied by R double prime by AC. This is equal to the temperature difference. Tf at x is equal to L minus T. AC cancels off, which is precisely why we want to write it this way. And it doesn't make any difference if it doesn't cancel off, we can calculate it. It's the surface area of cross-sectional area of a circle. R double prime is known to me. Tf is an exponential function, so this is going to be minus K R double prime. I'm doing the differentiation of Tf, which was originally written as the following, just for reference. T infinity, C3, C4. Differentiate this, substitute x is equal to L, then take this creature, substitute x is equal to L on the right hand side. So this is going to be C3 M e to the power ml C4 m e to the power minus ml, because I'm differentiating dt by dx and then substituting x is equal to capital L. This is equal to, big bracket start, T infinity plus C3 e to the power minus plus ml, e to the power minus ml. This is the temperature of the fin at x is equal to L minus 100 degrees. All of them are in Celsius, so we don't need to worry about things. All we have to do is substitute, isolate this thing. So in all these problems, the biggest area of issue is this algebraic manipulation. You make a small mistake here or you make a small mistake there, everything is gone. This is the place where you need to be careful. And this is the place where I do not have the luxury of spending time and showing you how to do things in the class. You have to go with the flow. I'm going to write out the final form of this. Okay, so this is what you'll end up getting. So substitute for M, L, 0.05, thermal conductivity K is 100, not a double prime, 4 times 10 to the power minus 4, and T infinity is 20 degrees Celsius. This will end up giving you the formula. Okay, so I'm going to write it out here. It's 81.8 C3 minus 0.06 C4 is equal to 80 degrees Celsius. The 80 comes from the fact that it's 20 minus 100, so that's minus 80. Shift around things, you get plus 80. Okay, so this is equation number 4. I'm going to list the other 3 which we had before. First one was minus 0.05 C1 plus C2. Then the second one was relating the temperatures. So I'm going to have C3 plus C4 was C2 minus 20. This was the equation 2, if I believe. And the equation 3 was a simpler one, just the flux balance. C1 is where I substituted for little m. 4 equations, 4 unknowns, solve it. This is what you'll end up getting. Okay, so C1, C2, C3 and C4 minus 2712 degrees Celsius. This is mundane work, okay? There's no thinking involved here, you just have to be careful. The thinking part is already done. C2. This is per meters. And then C3 and C4 are the following: 1.01 degrees Celsius and then 43.6 degrees Celsius. Okay, I'm going to get rid of this as well. To draw the temperature profile without any calculations. You can of course do the substitution, plug all the numbers into MATLAB, and then it will spit out the profile, but there's no fun in that. Minus L, 0, plus n. Okay, so these are the 3 things that we have. Here is the plane wall. This is the fin. At the interface between the fin and the wall, T fin is equal to T wall. The flux is also the same, minus K fin is minus K embedded portion. Because of the fact that the thermal conductivities are the same, the slope is also going to be continuous there. Plane wall is linear. It was at 200 degrees Celsius, so it's going to drop down linearly. This is 200. The temperature at the other end is 100. So I know that the direction of heat transfer is going to go from x is equal to minus L to x is equal to 0 onto the fin. That's the purpose of the fin. It's going to cool things down. But we also notice that the other end of the fin is contacting this other surface, and since this is a cooling fin because it's open to the ambient atmosphere, there has to be some cooling taking place. So there is bidirectional flow of heat from x is equal to 0 to plus L. I'm going to see a point where the slope of the temperature profile becomes 0. It is all through exponential. The fin profile is exponential. We just obtained it. We wrote it somewhere down. Okay, so somewhere here, this is exponential, but it's going to have a 0 slope. Question?
Never mind, I stopped.
Okay. It's an exponential profile, so continuous slope. This is continuous, there is no discontinuity. It might look like I have drawn it that way, so this is continuous. You can figure out where the slope becomes 0 by doing the following. It's a problem in algebra. You can do the derivative test and figure out where the slope is 0. So to do that, dpf by dx at this location, I'm going to call it as x star, is equal to 0, solve, and I'll be posting this in my lecture notes. If you solve, this gives you around minus 0.03 meters or 30 millimeters. X star is approximately 0.03 meters, positive. And this makes complete sense. The presence of the fin is to cool things. So which means that if the fin is in contact with the plane wall, the direction of heat transfer is from the wall to the fin. Hang on. If the fin is in contact with the other surface there, which I did not know to begin with was hotter than the fin or colder than the fin, I assumed it to be colder than the fin. But after I plot the profile, you will get the following shape, and this signifies that the heat direction of heat transfer is coming in from this surface onto the fin, and at a particular point, there is going to be energy balance taking place. The two fluxes will cancel each other off, and this is the point where the slope becomes 0. Question?
So when we assume that heat transfer is coming back from the other side, if you got a negative answer for your thing, then that would it ever hit 0 then? The slope?
So I should be getting a negative answer. If I calculate the heat flux here, I should be getting a negative answer. Because I had previously assumed that the direction of heat transfer was from the fin onto the other surface, you see.
If you assume that and you get a positive answer, then there is no...
Then something fishy is going on. Then there is a problem. Then the fin is not doing its job. And that's highly unlikely because this is designed as a cooling fin because the temperature of the ambient is lesser than the temperature of the surface. And so it has to take in heat from the surface, you see. Okay? Alright, so this is the temperature profile. The flux is more interesting. I have 5 more minutes left. Can somebody tell me, okay, without doing any calculations, once again, just draw my plots. is Q double prime, this is temperature. And if you're in doubt, just put all these into MATLAB and see what the answer is. Right? This is minus L, 0, plus L. Flux through the plane wall, is it positive or negative? Yes.
Positive.
Has to be positive, right? Because the wall is hotter than the fin. Is it constant, linear, quadratic, or cubic?
Constant.
Constant because the temperature profile is